Hello everyone, this is Niraj Kishore, a research scholar at MNIT Jaipur, India. My topic is a novel three-phase multi-level inverter cascaded by three-phase two-level inverter and two single-phase boosted H-bridge inverter. The outline of the presentation is the framework and backgrounds, profile topology, development of logic levels, results, conclusion, and references. Framework and background. Multi-level inverters are the most innovative and advanced power electronics converters, which are preferably opted by researchers in industry and academia due to its simple structures, modularity, less voltage stress across the switch, low total harmonic distortions, less switching frequency, low output filter volume, and low electromagnetic interference. However, MLIs have some limitations, such as the requirement of large number of power electronic devices, large number of gate driver circuits, and DC sources, etc. This is my profile topology. It is a cascaded three-phase inverter which consists of three main power modules. One is BHBI11, BHBI22, and TTI. VHBI is boosted H-bridge inverter and TTI is three-phase two-level inverter. BHBI11 is cascaded with TTI at phase A and B, and BHBI22 is cascaded with TTI at phase B and C, which generates a three-phase balanced output voltage. VHBI11 and VHBI22 is cascaded with TTI at a phase difference of 60 degree. Development of logic levels. Here, a modified reference signal is compared with level shifted carrier signals to get C0, C1 and C2, and these comparator outputs C0, C1 and C2 are used to develop a logic levels, that is L0, L1, L2 and L3 for different voltage levels. This is the simulation result for generating the line voltage VAB. Here V11 is the output voltage of VHBI11 and VAB is the output voltage of TTI. So these two output voltages are cascaded to form the line voltage VAB. This is the simulation result for line voltages VAB, VBC and VCA. So we get three-phase balanced line voltages on cascading BHBI with TTI at a phase difference of 60 degree electrical. This is the simulation result for line voltages and line currents, and from the simulation results we can see that we are able to generate balanced three-phase line voltages as well as balanced three-phase line currents for a particular load. Here 9 level output voltages are generated with the help of modified reference signals and level shifted carrier signals. Here we have also applied a pre-development techniques to reduce the THT as well as the voltage ripples across the switched capacitors. This is the simulation results for a voltage across the switched capacitor VC11, and from this simulation result we can see that the voltage ripple across the capacitor is reduced to less than 20% with the help of PWM techniques. This is the FFT analysis for the line voltages, and this is the FFT analysis for the line currents for a particular load. From this FFT analysis we can see that THT in the line voltages are reduced to 9.32%, and in the line current the THT is reduced to 4.85% for a particular load. All the simulations are done in MATLAB Simulink environment for these parameters. The DC source we have taken is 100 volt, the switched capacitor having capacity of 1 millifarad. We have taken RL load having resistance of 50 ohm and inductance of 10 millihenry. We have operated the switches at 5 kilohertz and we are getting the output voltages as 288 volt RMS at 50 hertz. This is the detailed comparison of the existing topology with the proposed topology, which is cited in this paper as a reference to 11, 12 and 13. Here NVL stands for number of output voltage levels, NAS stands for number of active switches, NDC stands for number of DC sources, R stands for ratio of number of switches to the number of output voltage levels, and NC is the number of capacitors used. In the proposed topology, I have used 22 active switches, 3 DC source and 4 switched capacitor to generate 9 level voltage. So active switched in proposed topology used are less than remaining the other topologies.